You should not exist. That is not a metaphor, and it is not a line of philosophy. The most solid, most precisely tested equations physics has ever produced say that this universe should contain no stars and not a single atom of your body. The math is on the table, and the math is merciless. The universe should be an endless, empty sea of light with nothing floating in it. A stillborn universe. But here you are. You are breathing. You are hearing this sentence. And for nearly 100 years, science has been unable to explain how that is possible. Everything in the universe, you included, is the remainder of a calculation that refuses to balance on paper. If this is your first time here, subscribe. Because by the end of this, you will understand why you should not exist, and why the thing that kept you here is still a mystery no one has solved. And this is no dusty textbook debate. The calculation is being interrogated right now, these very months. In 2026, CERN announced new measurements. The LHCb experiment, about 100 meters beneath Geneva, used the first data from its completely rebuilt detector to remeasure the famous angle that describes the difference between matter and antimatter, the gamma angle, and released the results. That same year, new evidence for this difference was published in An Entirely Different Decay of the Particle Family That Builds the Universe, which means that, while this sentence plays, protons are colliding millions of times per second beneath the ground, and physicists are chasing one single thing inside those collisions. The answer to why you exist. They have not found it. And the reason they keep searching is that everything about to be told here is still an open wound. To see the question itself, you have to go back to 1928. That year, a young physicist named Paul Dirac wrote an equation describing the behavior of the electron. The equation worked flawlessly. It explained in one stroke things no one had been able to explain before. But there was an uninvited guest inside it. The mathematics of the equation demanded the existence of a twin, identical to the electron in every way, but carrying the opposite electric charge. Something like your reflection in a mirror. Everything the same as you, but reversed. Dirac was unsettled by his own equation's insistence, and for a while he tried to explain the twin away using known particles. It did not work. The equation refused to back down. And 4 years later, in 1932, Carl Anderson caught that particle for real while studying the tracks of cosmic rays arriving from space. The electron's anti-twin, the positron, was sitting right there on the photographic plate. The ghost on paper was real. Antimatter existed, and no one had imagined it. Mathematics had forced it onto the table, and it did not end with the electron. In 1955, the accelerator at Berkeley caught the proton's anti-twin, the antiproton, and the others followed. Slowly, it became clear that this was not an exception, but a basic feature of the universe. Every known particle has a dark twin. As if behind the periodic table, there stands a shadow table, identical in every detail but turned inside out. And this shadow is not half finished either. Bring an antiproton and a positron together, and you get an atom of antihydrogen. An atom that looks no different from real hydrogen. On paper, it goes further. Anti-molecules built from anti-atoms. Anti-stars built from anti-molecules. Somewhere far away, an anti-you, seeing their own reflection when they look at you, would break no law of physics. And this is where the truly unsettling question begins. If nature always creates these twins in pairs, where did half of them go? Contrary to the science fiction films, Antimatter is not some distant laboratory curiosity either. A PET scan at a hospital works by giving your body a substance that emits positrons, and that is exactly what the P in the machine's name stands for: positron. The banana in your kitchen fires off a single positron roughly every 75 minutes because of the natural potassium inside it. Even inside your own body, right now, antimatter is occasionally being born. So with all this antimatter appearing around you, why do you never notice any of it? Because it dies the instant it is born. When a particle meets its anti-twin, both of them cease to exist. They do not slow down. They do not scatter into smaller crumbs. They are erased completely, and what remains is pure light, like 2 drops of water merging and evaporating, but far more absolute. After the meeting, nothing remains to say those 2 particles ever existed, only a flash. This is where Einstein's famous equation takes over. The entire mass is converted into energy, with no loss at all. If 1 gram of antimatter met 1 gram of matter, the energy released would equal several Hiroshima bombs. An ordinary bomb converts only a tiny fraction of its mass into energy. Annihilation converts all of it, 100%. It is the most efficient form of destruction known in the universe. If you and that you mentioned a moment ago ever met and shook hands, the energy released would surpass the combined total of every nuclear weapon humanity has ever detonated. A single handshake. That is why antimatter is not only the most dangerous substance in the universe, but also the most fragile. In our world, it can be kept in no container because everything it touches is its executioner. And in a moment, you will see this form of destruction running at an unthinkable scale in the first second of the universe. Because when energy turns into matter, nature enforces a rule that allows no bargaining. Matter is never born alone. Whenever particles are created from pure energy in a laboratory, the anti-twin is born alongside, without a single exception. In 100 years of experiments, every single time, a pair. This rule is not an assumption. It is daily routine. It gets tested billions of times a day in accelerators around the world, and it has never once been broken. Nature works like an accountant who counts every last coin when it comes to matter. Whenever it writes a particle into the ledger, it writes the anti-twin into the opposite column, and the 2 columns stay equal at every moment. Now take that accountant and put them in charge of the largest transaction in history. The Big Bang was, after all, an enormous amount of energy turning into matter. So in that first moment, equal amounts of matter and antimatter must have been born. And you already know what equal amounts means. It means total annihilation. Every particle finds its twin sooner or later. Every meeting erases both sides. No one survives because the scale is perfectly balanced, and the ledger closes at 0. Nothing remains. Not a single proton to build the stars, and not you, nothing but light. The most basic rules of physics predict this. The universe should have been an empty glow, cooling forever. Try to picture that universe. You cannot, because there are no eyes inside it. Light expanding toward infinity, cooling and thinning, flowing on without striking anything, without illuminating anything. There is no surface for it to fall on, and not a single consciousness to know that light exists. Time passes, but it passes for no one. This is the universe, physics predicts. Perfect, balanced, and absolutely desolate. In the eyes of the equations, our universe, the one with mountains, oceans, and you in it, is a strange deviation that breaks the rules. Your existence is not the fulfillment of a prediction. It is the collapse of one. But here you are, so somewhere the calculation went wrong. Now look around. To feel how strange this is, imagine the following. Picture an enormous ballroom holding 1 billion pairs of dancers. The rule is simple. Whenever the two members of a pair meet, both vanish on the spot. The music starts. The pairs meet one by one, and with every meeting, the hall lights up in a flash and empties a little more. When morning comes, a single person is standing in the middle of the hall. Their partner never came. That is exactly what happened in the first second of the universe. Out of every billion matter-antimatter pairs, only a single particle of matter survived. The rest, those billions of pairs, destroyed each other into light. Everything you see today was built from the ones left standing alone. The stars and your own hands, remnants of the same slaughter. The number of atoms in your body is a 28-digit number, and every one of those atoms, one by one, is a dancer whose partner never came. You are a rounding error of 1 in a billion. The ash of that slaughter is still here too, and far closer than you would guess. In today's universe, for every particle of matter of the kind you are made of, roughly 1 billion photons wander loose. Those photons are the cooled remains of the flash from that great annihilation in the first second. It is called the cosmic microwave background, and it has been raining down from every point of the sky, without pause, for 13.8 billion years. It is raining right now. It passes through this room. It strikes your skin. Part of the static you used to see on old analog televisions, on channels with no signal, was that as well. The ashes of your twin fall on you every day, and you live without ever noticing. Every time you look up at the sky, you're not looking at the site of a victory, but at the field of a war in which both sides very nearly died out completely. That darkness between the stars is not empty. It is full of that light, and that light is what remains of a massacre your own side survived at a rate of only 1 in a billion. So how did that 1 in a billion survive? If the scale was perfectly balanced, not a single particle should have been left over, which means the scale was not perfectly balanced. The first person to put this idea seriously on the table was someone you would never guess. Andrei Sakharov, the man who built the Soviet Union's hydrogen bomb. A man who spent 1/2 of his life building a weapon that could turn matter into energy and erase cities, sat down in the other half and asked, then why is there matter in the first place? The man who knew the mathematics of destruction better than anyone turned to the mathematics of existence. In 1967, in a short paper, he wrote down one by one the conditions required for matter to be left over in a universe. At the heart of the list stands a single item. Nature cannot treat matter and antimatter exactly equally. Somewhere, however small, the rules must lean toward matter. Without that lean, the ledger closes at 0, and no one ever exists to speak this sentence. The problem was this. Everyone believed that scale was flawless. The belief even has a name: CP symmetry. Think of it this way. Film the universe, then replace every particle in the film with its anti-twin, and watch the scene through a mirror. CP symmetry says the laws of physics should not notice the change. The two films should run identically. Matter and antimatter should be perfectly interchangeable in nature's eyes. An elegant and flawless rule, and nature was caught red-handed breaking it. In 1964, at Brookhaven Laboratory in America, James Cronin and Val Fitch were watching the decays of short-lived particles called kaons. The expectation was clear. The mirror rule would hold in every decay. It did not hold. roughly 2 in every 1,000 decays happened in a way that should have been impossible. 2 in 1,000. A tiny deviation, a flaw that could easily have been overlooked. But in physics, there is no such thing as a small violation of the forbidden. Those 2 in 1,000 were the first proof that nature can tell matter and antimatter apart. The mirror had cracked. The result was so unexpected that the physics world first went hunting for a mistake. Instruments were checked, measurements were repeated. There was no mistake. Nature, at its deepest layer, was favoring one of the two twins. The discovery later brought Cronin and Fitch the Nobel Prize, and more important than that, it opened a door, for the first time, to the possibility of your existence. So the scale could lean. So the favoritism Sakharov was looking for was no fantasy. Nature had been caught holding it. But there is a strange side to this favoritism, and it cannot be passed over. 1 in a billion. Why not 0 is now understood. The scale leans. But why not half and half? Why not 1 in 10? If nature decided to favor matter, why did it favor it so reluctantly? By such a razor-thin margin. Had that ratio been slightly smaller, the leftover matter might not have been enough to ignite the stars, and the universe would have stayed dark after all. Slightly larger, and an entirely different universe would have been born. Your existence depends on a scale nobody calibrated, leaning at exactly the angle that makes this universe possible. And every physicist who asks why that angle is that angle still hits the same wall today. But inside that crack hid a problem that no one managed to close for the next 60 years. And this problem concerns your body directly. Because from that day on, every particle caught breaking the mirror belonged to a type called mesons. Mesons are brief, unstable unions of one quark and one antiquark, born in colliders, dead in less than a trillionth of a second. You were not made for mesons. Your body, and every star in the sky, nearly all the visible matter in the universe, is made of baryons, particles built from 3 quarks coming together, meaning protons and neutrons. And baryons, the family of matter that makes you you, had never once been caught breaking the mirror. The search ran for decades. Experiment was built upon experiment. Data piled upon data. Nothing came out, as if the very matter that builds the universe were keeping silent to protect its own secret. That silence broke in 2025. The LHCb experiment at CERN observed, for the first time in history, the family of matter you are made of behaving differently from its anti-twin, and the results were published in the journal Nature. A wait of 61 years ended with a single measurement. The headlines called it a triumph, and they were right. It truly was a historic moment. But inside that measurement, there was a bitterness that mostly never reached the headlines. Because the difference that was found was measured, weighed, and placed against the universe's accounts. And the accounts did not balance. What was found was both one of the greatest victories in the history of physics and the thing that pushed the door of the real question wider open than it had ever been. Behind that door stands one fact. Whatever saved you, we still have not found it. And how deep the gap runs only becomes visible when you look closely at the numbers of that measurement. The hero of that measurement is a particle almost no one has heard of, the lambda B baryon. Think of it like this. Take a proton, remove one of its quarks, and put in its place a far heavier, far more unstable quark, the kind called a beauty quark. What you are left with is a heavy, restless cousin of the proton. This particle doesn't live long It decays in less than a trillionth of a second and falls apart. What remains is one proton, one kaon, and two pions. On its own, an ordinary event. But this decay also has a mirror version. The anti-lambda b, its twin, falling apart into the anti-versions of the same pieces. If CP symmetry were flawless, these two decays would be exact reflections of each other. The same frequency, a perfect balance. What LHCb did was put that balance on the scale. To do it, the detector recorded proton collisions for years. The scale of this is hard to grasp. In the ring beneath the ground, beams of particles pass through each other millions of times per second. Every crossing creates a cloud of debris, and the detector photographs every one of those clouds. The decay being hunted is not even a needle in a haystack among those photographs. It is one specific straw in the haystack. Physicists sifted these decays one by one out of that enormous pile spread across years. Tens of thousands of lambda b, tens of thousands of anti-lambda b. Then they counted. The number spoke with a clarity rare in physics. The matter, lambda b, and its anti-twin were not performing the same decay at the same rate. The difference between them was 2.45%. That sounds small, and that is the trap. What matters is not the size of the difference, it is the certainty. The statistical strength of the measurement was 5.2 sigma, meaning the chance that this difference is a coincidence, a trick of the data, is far below 1 in a million. In physics, the official threshold for calling something a discovery is 5 sigma, and this measurement crossed it. The result was published in Nature in 2025. Exactly 61 years after the first crack in the mesons, the type of matter that builds the universe, the baryons, had been caught breaking the mirror for the first time. The family you are made of is, in nature's eyes, different from its twin. This is no longer a theory, it is a measured fact. There is an even more striking layer to this. The decay does not proceed along a single path. As the pieces fly apart, there are different waypoints, different energy regions, and the difference is not spread evenly across them. When physicists scanned the map region by region, they found corners where the asymmetry climbs above 5%, and with a certainty beyond 6 sigma. So nature is not committing this favoritism in some hidden, faint corner. Under certain conditions, it does so openly, with a measurable appetite. That the scale leans is no longer in dispute. What is in dispute is where this lean comes from, and why something this important is this small. And the file did not close there. It accelerated. At the end of 2025, LHCb announced the most precise value yet of the gamma angle, the angle that describes the difference between matter and antimatter, roughly 63 degrees, with an uncertainty smaller than 3 degrees. Then in 2026 came the first gamma result from the Run 3 measurements, the first data collected with a completely rebuilt detector, roughly 68 degrees, consistent with what came before. And the rebuilt machine is so powerful that with only 4 months of data, it caught more signal than the old detector, gathered in years. In the same period, in an entirely different family of lambda b decays, the ones containing the JPSI particle, new evidence for the violation was published with a strength of 3.9 sigma. These dates say one thing: this is not a closed file. This question is being measured at this very moment. Most of the great questions in the history of science are spoken of in the past tense. This one is spoken of in news bulletins. And every new measurement, every shrinking margin of error, sharpens the same unsettling picture a little more. To see what that picture is, you first have to understand what the gamma angle actually measures. Physicists draw the rules by which quarks turn into one another, the machinery where the difference between matter and antimatter is born as a triangle. Every measured quantity gives one side or one corner of that triangle. The rule is simple. If the theory is right, then when all the pieces from different experiments come together, the corners of the triangle must close exactly. If a corner stays open, it means someone invisible is standing in the drawing. A new particle or a new force the standard model does not know. The gamma angle holds a special value for physicists. It is the corner of the theory that can be measured with the fewest assumptions from the cleanest processes. Gamma is like the incorruptible witness of the calculation, even if everything else were mistaken. Gamma tells you what nature is actually doing, which is why every new gamma measurement is really an exam. Does the triangle close, or does it not? So far, it has closed. Every violation ever measured fits the mechanism built in 1973 by two physicists named Kobayashi and Maskawa, meaning the standard model's own internal arithmetic. Even that 2.45% difference in the baryons sits within the theory's predicted range. The theory passes exam after exam. And that is exactly the bad news. Why bad news? Because now, gather everything in hand. Take every violation found in 60 years, from those 2 in 1,000 in the kaons to that brand new difference in the baryons. Place it all in the first second of the Big Bang and run the calculation. How much leftover matter does this much favoritism produce? The calculation runs and a number comes out. But the number that comes out falls short of explaining the universe we observe by whole orders of magnitude. Not by a little, but by a factor of billions, roughly. Think of it like this. The debt that must be paid for the universe to exist is 1 billion gold coins. And after 60 years of searching, what we found under the couch is a single copper coin. The coin is real. It shines, and it is in our hand. But it does not pay the debt. It does not even come close. That nature favors matter has been proven, yes. But the favoritism we have proven is so feeble, it could not hold up a single galaxy in this universe. It could never bring you into existence. Here is the translation of this into your daily life. Every surface you are touching right now, and the air you are pulling into your lungs, rests on an exception whose reason we do not know. The building looks solid enough, but the blueprint of the foundation is missing. Gaps like this have always existed in the history of science, and most of the time, they were thrilling, because an opening means a continent waiting to be discovered. But this gap stands somewhere different. This is not a distant star behaving oddly, or the decimals of some constant refusing to line up. This is the existence of anything at all. The question being asked is the most basic question in the universe, and the whole of verified physics is silent before it. And add this: the violations we have found are not just insufficient, they are also the violations the theory already expected, meaning the standard model is displaying its own predicted cracks, and no universe comes out of those cracks. The meaning is naked. The mechanism that brought you into existence is not inside verified physics. The most successful theory we have, the structure that describes the inside of the atom with staggering precision, falls silent before the fact that you exist. You are a data point that humanity's finest equations cannot carry. So what saved you? The honest answer: nobody knows. There are candidates, but listen with a warning, because from here on, this is not proven science. it is speculation, under test. The most discussed candidate is the neutrinos. These are the quietest particles in the universe. They interact with almost nothing. Most of them would pass without stopping through a wall of lead, even if it were a light year thick. Trillions of them are passing through your body every second right now, and you feel nothing. The answer to the universe's greatest question may be hiding in these ghosts that are nearly impossible to see. Some physicists think this is where the scale truly leaned. In the early universe, neutrinos and their heavy relatives favored matter, and that favoritism was later handed down to the matter we know. The first hints from neutrino experiments point toward a violation in this direction, but none of it is confirmed yet. Another candidate is entirely new particles the standard model cannot see, physics hiding at energies our colliders cannot yet reach. And there is a third possibility, the one physicists like least. Maybe the imbalance was born from no mechanism at all. Maybe it was simply there from the start, in the explosion itself. That is not an explanation. It is giving up on explanation. But right now, we do not possess a single measurement that could say which of these three is true. There is one more possibility, maybe the one that seems most reasonable to you. What if the antimatter never vanished at all? What if it is simply somewhere else? Galaxies built from antimatter stars, shadow regions living their own lives at the far end of the universe. On paper, a clean way out. But the sky refuses it. Every border where a matter region touched an antimatter region would be forced to glow with a continuous annihilation radiation, like a giant fence woven from gamma rays across the sky. Telescopes search for that glow and find it nowhere. The universe we observe appears to be made of matter all the way to its edges. That left one last hope. Maybe gravity treated antimatter in reverse. Maybe it pushed it away. And in the universe's first moments, the two sides separated and withdrew into their own corners. In 2023, another experiment at CERN sealed off that last hope too. Physicists produced antihydrogen atoms inside a magnetic trap. Remember, antimatter can be kept in no container. You can hold it only in midair, touching nothing, on the tips of invisible magnetic fingers. Then they slowly loosened the trap and watched where the atoms went. Antimatter, just like matter, fell down. Gravity does not push it away, does not sweep it into some separate corner and hide it. The antimatter did not escape, and it is not hiding. It died right here, in the arms of the matter you are made of, in the first second of the universe. Now, hear this at your own scale. Every particle in your body had an anti-twin in that first second. Not as a metaphor, in the full meaning of the word. A twin, tuned to it, down to its mass, and its charge, ready to turn both of them into light, the moment they met. Those twins met others and were erased. Yours were never erased. The past of every surviving particle is the same. 1 billion of its siblings turned to light in that first second. It did not. Then, those survivors were cooked inside stars, hurled into space by explosions, and gathered on a planet. And at the very end, 13.8 billion years later, some of them became your heart. Every beat of your heart is the work of particles that did not die in that first second. Which rule spared them? Why this proton survived instead of that one, no equation can say. The most precise measurements in the history of science and its brightest minds have gathered around this question, and the question's official answer today is a single word: unknown. The only identity physics can hand you today is this: an unexplained accounting remainder of 1 in a billion. Right here, the matter has an important subtlety, because this is not the kind of gap someone will patch tomorrow with a small correction. The measurements are real, the difference in the baryons is real, and the insufficiency is just as real. If the problem were a measurement error, it would have been found long ago. Think of how many generations of physicists have gone over this calculation in 60 years. The problem runs deeper. The existence of the universe requires something beyond the whole of verified physics. That is also why physicists are so obsessed with hunting for cracks in the standard model. If that triangle one day fails to close, if one gamma measurement one day disagrees with the others, it would not be a catastrophe. Quite the opposite. Wherever the theory is wrong, that is where the reason for your existence is hiding. And the vice tightens every year. The margin of error on the gamma angle was once measured in tens of degrees. Today it is below 3, and as the data from the rebuilt detector grows, physicists aim to push it below 1. As the margin shrinks, the theory has fewer places left to hide. Either the corners of the triangle will close perfectly, in which case, we will have to accept that the answer lies entirely outside the standard model, perhaps somewhere we can never reach. Or one day, one of the corners will not close, and that tiny opening will be the first light of new physics. Both possibilities are on the table, and in both of them, the explanation for your existence stands somewhere outside everything currently known. The collisions have not paused for this video. In the ring beneath Geneva, protons are still striking one another millions of times per second, and every collision restages that first moment at a miniature scale. Energy turns into matter. Twins are born in pairs, and the instant they meet, they turn to light and are erased. Physicists watch that scene frame by frame, chasing one thing: the flaw. The moment when the scale secretly presses down on matter's side, when the two columns of the ledger, for one instant, fail to come out equal. Because somewhere inside that flaw is written the reason the stars burn and the reason your heart beats. Every flaw found so far has given the same answer: real, but not enough. The true flaw is still out there somewhere, maybe in the next dataset, maybe at an energy we will never reach, and maybe the true name of the fear this video has been describing only becomes clear now. This is not a fear of destruction. It is a fear of destruction without a trace. Exactly half of the universe, the whole of antimatter, was erased and left almost nothing behind, only a cold light scattered across the sky. And the same fear, step away from the universe's smallest scale, is standing right under your feet. You assume you are the first owner of the ground you are standing on. But what if you are not? Millions of years before you, an entire civilization may have come and gone on this planet, and the earth may have ground up and swallowed every trace of them, and you could never know. That question waits for the next video. This video's last word, though, belongs to its own question. The universe's ledger still says 0. By the rules, there should not be a single star in the sky tonight, and there should be no ear hearing this voice. Light should have remained, nothing but light. But you remained. A surplus of 1 in a billion. An accounting error asking itself why it exists. And if the answer to that question is ever found, it will not be found in a library, but in that tunnel beneath the ground, at the point where two beams of light collide. Until that day, your existence remains what it is: a surplus standing in the middle of the universe's best understood equations, one that no one can erase and no one can explain. You are here, and still no one knows why.